Hello, my darlings. Okay, so today we're going to talk about antiderivatives. So far, for the most part, we've been finding derivatives. If I give you a function f of x equals x cubed, you take the derivative, and f prime of x is 3x squared. Antiderivatives, we go the other way. We start with the derivative, and we find the function. So we find f of x if we know that the derivative f prime of x is 3x squared. Then we can say that the function is x cubed. Now, is an antiderivative unique? Meaning, does it have only one answer? And the answer to that is no. For instance, let's take a look at f prime equals 2x. If we have f of x equals x squared, this has a derivative of 2x, but so does x squared plus 2, and so does x squared minus 5. Okay, so that means, therefore, if dy dx, or f prime of x, equals 2x, then y, or f of x, equals x squared plus some constant c. And the general standard accepted variable is c for that constant. That's what everybody will recognize, okay? Now, a couple of terms here. If we know that capital F prime of x equals lowercase f of x, so f prime of x equals f of x, then for all x belonging to the interval I, we say capital F is the antiderivative of the function f over the interval I. Also, we call that antiderivative f of x plus c the general antiderivative, and c the arbitrary constant. So each function has an infinite number of antiderivatives. So that's why that plus c, that's the general antiderivative. Okay, let's take a look at an example. If we know that dy dx equals 4x cubed, how do we find the antiderivative? Now, when we take the derivative, we would multiply by the exponent and subtract 1 from the exponent. When we do the antiderivative, we do the opposite. Remember, derivatives and antiderivatives are going to be like inverse functions. So we're going to do the opposite operations. Okay, we're going to take what we had, 4x, but instead of cubed, we're going to add 1 to that exponent, which means we also have to divide by that exponent, and don't forget your plus c. So that means when we simplify it, y equals x to the 4th plus c. And yes, once you get good at this, you're going to jump right to that step. Not a problem. If dy dx equals x to the 4th, what had that derivative? Well, we would have to raise the exponent by 1, and we're going to divide by 5 plus c. There is our antiderivative. So in general, if dy dx is x to the n, then the antiderivative y is x to the n plus 1, add 1 to the exponent, divided by our new exponent, plus c. There you go, your first antiderivative rule. Let's try a couple problems. Okay, so let's say we have dy dx equals x to the 8th minus 2x to the 4th. Well, the antiderivative dy dx is y. For x to the 8th, we raise that exponent by 1 to 9 and divide by that new exponent 9. Minus, we had 2x to the 4th, but I'm going to add 1 to the exponent, so it's 2x to the 5th. I'm going to divide by that new exponent, and I'm going to add c. There we go. Well, how about this one? Dy dx equals 5. Now, there's no exponent on the x, right? But it's a constant. What has a derivative of just a constant? Well, that must have been 5 times the number x, and it could have had a constant here. Now, another way to think about this, dy dx is 5 times x to the 0. So when we find the antiderivative, we add 1 to that exponent and divide by 1, and that's the same as what we just did. Okay, so it does follow the same rule. Well, what if dy dx is 0? What kind of functions have derivatives that are 0? The only kinds of functions that have derivatives of 0 are horizontal functions. They are the constant functions. So that means that y equals some constant c. That's it. And that's a good rule of thumb there, that if dy dx is 0, then the antiderivative is y equals a constant. Okay, now we have dy dx equals x to the 2/3. So what has a derivative dy dx? That's y. Now x to the 2/3, I'm going to leave a little space, I'm going to write my x. Now 2/3 plus 1, 2 plus 3 is 5 over, keep the denominator 3. Now when we divide by this exponent 5/3, dividing by a fraction 5/3 is the same as multiplying by the reciprocal 3/5. And then, of course, we're going to remember to add our constant. Good. Okay, let's take this one step further. Yay, she's bringing trig into it. Oh no, I hear the groans and the eye rolls. Okay, if dy dx equals cosine x, what has a derivative cosine x? Y equals sine x, and don't forget that plus c. If dy dx equals sine x, then y equals, what has a derivative of sine x? Not cosine x, but negative cosine x, right? Because the derivative of cosine x is negative sine. So we need to negate that, and don't forget your plus c. Now dy dx is secant squared x, then y equals, what has a derivative of secant squared? That's tan x, and don't forget the plus c. Now if dy dx equals cosecant squared of x, then y equals, what has a derivative of cosecant squared x? Not quite cotan x, but the negation of the cotan x, plus c. If y equals secant x tan x, then what's y? What has a derivative of secant x tan x? That's y equals secant x, and don't forget your plus c. And the last one in this box, if dy dx equals cosecant x cotan x, then y equals negative cosecant x plus c. Now I know you're looking at this and going, oh my goodness, Mrs. Williams just gave us 6 more rules to memorize. No, they're the same as the derivative rules you already know. It's just going backwards. They're the same rules. Please do not panic, okay? Let's look at the next problem. If dy dx equals sine 5x, then what's y? Well, here's the catch. We know that y has a derivative of dy dx. Well, what has a derivative of sine? That would be negative cosine. Keep the angle 5x. Now check this. If you took the derivative of negative cosine of 5x, you'd have positive sine of 5x, but you'd have to multiply by the derivative of the inside, which is 5. So we need to divide by that derivative of the inside 5 plus c to take care of that chain rule, okay, because we didn't have that constant. Now, that answer's okay, or a lot of people will prefer to write it as negative 1/5 times cosine 5x and plus c. They're both the same. I'm perfectly happy. Now, think about what we just did with dy dx equals sine 5x. Now we have dy dx equals cosine nx. N is just a constant. What has a derivative dy dx? That's y. What has a derivative cosine x? That is sine, and we keep the angle. But what's the derivative of the angle nx? It's n, so we're going to divide by n, because we didn't have that over here. So we must have divided it out, plus a constant c. There we go. All right, just a couple more problems to try. We're going to find the general antiderivative of the functions below. So the first one, x to the 5th minus 6x plus 3. So x to the 5th, we add 1 to the exponent, so it's 6. Divide by that new exponent. Minus 6x, add 1 to that exponent, so it's squared. Divide by that new exponent. Plus, now we just have a constant 3, so that must have been 3x. Don't forget your plus c. And we can do a little bit of simplifying here. X over 6 minus 6 over 2 is 3x squared plus 3x plus c. And yes, ladies and gentlemen, I do want them simplified. I do not want you leaving minus 6 over 2x squared. Okay, let's look at b. Negative x to the negative 3 plus x over negative 1. So we're going to have negative x. Now be careful. When you add 1 to negative 3, you get negative 2, and we're going to divide by negative 2. Plus, now we had x, so we're going to add 1 to that exponent, which was 1. 1 plus 1 is 2. Divide by that new exponent 2. Minus, if we have 1, remember that's like a 1x to the 0. So when we raise that exponent, it's now x to the first, or just x. Don't forget your plus a constant at the end. Now we can simplify this a little bit because we have a negative over a negative here. That's a positive 1/2 x to the negative 2 plus 1/2 x squared minus x plus c. Nice. There we go. Okay, now take a look at c. Before you find the antiderivative, you need to rewrite this. This is 1/2 times x raised to the negative 3. Now notice I did not bring the 2 up because that would mean I'd have the 2 and the x cubed but raised to the negative 1. That's more complicated. I do not even want to think about that, okay? Not at this point. So we're going to keep our constant 1/2. We have x to the negative 3, so we're going to add 1 to that exponent, so that's negative 2. Divide by that new exponent, negative 2. Don't forget your plus c. Now, we have here a 1/2 times a negative 1/2. That's negative 1/4 x to the negative 2 plus c. But where does a negative in the exponent tell you to write it? It tells you to write that x squared in the denominator. So here is our antiderivative. Remember, if I don't give you any negative or fractional exponents, you should not give me any back, okay? Practice the algebra, make sure we've got those skills down. Now D, okay, now that I've said that rule, I'm not going to follow through on the next problem, just because it's nasty. Okay, so before we take the antiderivative here, we want to look at what these exponents are. The cubed root of x is x to the 1/3 plus. Now 1 over the cubed root of x is still x to the 1/3, but we have to make that exponent negative so that it's in the bottom. Now the antiderivative of x to the 1/3, 1/3 plus 1, 1 plus 3 is 4, keep the denominator 3. But we have to divide by that exponent 4/3, which is the same as multiplying by 3/4. Then we're going to have plus x. Now negative 1/3 plus 1, negative 1 plus 3 is 2/3. And when we divide by 2/3, that's the same as multiplying by 3/2, and then plus c. And I'm going to let us stop here on this one. Let's look at e. Now we have negative 3/2 x to the negative 5/2. You notice I'm practicing the negatives and the fractions for you? Okay, so we're going to keep our constant negative 3/2. I'm going to leave a little bit of space. I'm going to have my x. I have negative 5/2 in my exponent. I need to add 1. So negative 5 plus 2 is a negative 3 over, keep the denominator 2. When I divide by that exponent negative 3/2, that's the same as multiplying by negative 2/3. Let's not forget our plus c. If you look at these constants, they multiply to 1. So this is just x to the negative 3/2 plus c. Good. Next up, we have pi cosine pi x. So we keep our pi. What has a derivative cosine? That's sine. Keep the angle, but remember, we divide by, what's the derivative of pi x? That's pi, and we're going to have a plus c, but you should see that those pi's are going to cancel out, and we're just left with the sine of pi x plus c. Yay! All right, 2 more. We're almost there, guys. Cosine of pi x over 2. What has a derivative of cosine? That's sine, and we keep the angle pi x over 2. Now, what's the derivative of that angle? Pi x over 2. The derivative is pi over 2, so we have to divide by that, which is the same as multiplying by the reciprocal, 2 over pi. And don't forget, plus c at the end. Good job. One more. What has a derivative of cosecant squared? Well, that's a negative, right? All our cofunctions have negatives. Negative cotangent squared of 7x. But don't forget, we have to divide by the derivative of that angle 7x. So we'd have to divide by 7, or I could just multiply by negative 1/7. It doesn't matter if I write it that way or if I write it this way. They're the same, but in both cases, I have to remember my plus c's. And it doesn't matter which one you use. All right, guys. So antiderivatives, remember, we're working backwards to find the function that has that derivative. These rules are our derivative rules. We're just doing the opposite operations. That's it. Okay, we're going backwards. All right, guys, have a wonderful day. I'll see you soon. Bye.